Much for the invitation. I'm very excited to be here and to share with you the Memorial Sloan Kettering experience of translating basic. Actually, there is a paradigm change for cancer treatment. Alongside with the traditional treatment options of surgery, radiation, chemotherapy, immunotherapy has become the fourth pillar of the modern cancer care. So immunotherapy uses the forces within our own body and re-educate the immune system for tumor specificity as well as memory. And CAR T-cell therapy is one of such examples of immunotherapy. I'm not going through the CAR, what it is in these slides. I use this one just to remind myself and the audience that since the conception of first-generation CAR in the late 1980s, we are here now have 6 approved therapies targeting 2 targets, CD19 and BCMA. And up to now, more than 30,000 patients has been treated with CAR T product, and over 250 companies are engaged in the development and application of cancer CAR T therapies, including Miltenyi. In addition to CD19 and BCMA, this table summarized the top 15 CAR targets, not just CAR T, but also CAR NK therapies. So include CD22, mesothelin, one of our previous speakers has mentioned, CD7, CD33, HER2, etc. So at Memorial, we have successfully completed 17 clinical trials under 11 IND, target 7 different tumor antigens for 7 broader disease implications. We currently have 4 ongoing clinical trials targeting 4 different targets for both hematological and tumor and solid tumor indications. We have 6 more CAR T therapy clinical trials alongside TCR-T and NK clinical trials in the pipeline. I want to share with you our journey of translating CAR T therapies from research to clinic. So it start off from Dr. Sideline's first report at Memorial by using the first generation CAR, the 19Z1. So if my cursor works, okay. So the first report from his lab is the irradiation of a Raji tumor from SCID beige mice using the first generation 19Z CAR. And quickly afterwards, he demonstrated that the second generation CAR, 1920Z, this one, has better anti-tumor activities. And we quickly translated these discoveries into clinical trials. So the first trial from Memorial was in 2006, which is designed for treatment of patients with CLL, and followed by another trial using the 1920Z design for patients with ALL. This is 2009. And patients enrolled in these 2 trials have been benefited from the treatment. But however, you can see that a fraction of the patients will relapse. So what could be the mechanism for relapse? We heard a little bit already earlier. So it could be cancer escape. It could be lack of persistence. It could be hostile tumor microenvironment. So the approach we took to increase the CAR T-cell fitness, I'm showcasing here, is by fine-tuning the activation strength through CAR T engagement of the tumor. So there are 3 items in the CD3 zeta domain. So item stands for immunoreceptor tyrosine-based activation motif. So we generated mutations by replacing the tyrosines with phenylalanines and generated single item mutants. So 1XX means the first item is active, X2X means the second item is active, and XX3 means the third item is active. So by testing these 3 different designs, by using a CAR-stressed model, also developed by Dr. Sadeline's lab, we treat the mice, the tumor-bearing mice, the NAM6 tumor-bearing mice with as few as 50,000 CAR T cells. And you can see that the 1XX mutant has displayed a more pronounced anti-tumor activity. So each line in here is actually the tumor. So we are looking at the fluorescence of the tumor. So 1XX is the most potent. We also observe that the tumor irradiation activity of the mutants decreases with the functional distal positioning of the design of these mutants, meaning that XX3 actually have the least anti-tumor activity. 1XX has the most anti-tumor activity. So what could be the reason for this? So we decided to look into the profiles, transcription profiles of these different CAR designs. So for the 1920Z, these first big columns with 3 lines, you can see that the wild-type 1920Z is more resembles to the T effector cell phenotype. And with the 1XX CAR, you can see in the middle, it more resembles to the T-stem central memory phenotype, while the XX3 is more like the T-naive phenotype. So we think that by fine-tuning the activation of the CAR, we have separated the T activation and differentiation. So by the 1XX design, we have preserved the memory-like phenotype, which can explain the better anti-tumor activity of the 1920Z 1XX CAR. So we also tried another approach to fine-tuning the anti-tumor activity of the CAR, which is through the decrease of the tonic signal of the CAR construct. So we used the CRISPR-Cas gene editing program in this approach. So what we did is, by using CRISPR-Cas9 and guide RNA, we disrupted the T-cell receptor alpha constant region and specifically incorporated the 1920Z CAR at the track locus by homologous recombination. So I want to bring your attention to the expression patterns of the retrovirally transduced CAR. You see the broad expression levels. In contrast that the track CAR, there is a very tight homologous expression. When testing these 2 different CAR designs in the mice, it's obvious if you look at the survival curve at the bottom, the blue line representing the track CAR design, and this track CAR is much more potent than the other CAR designs. So what could be accounting for this fitness improvement? So by looking at the CAR T cells and also tumor cells in the bone marrow at different time points, we get some illustration of the mechanism. So before I go there, I want to orientate you to which is which. So the blue indicated the track CAR design. The green is the conventional 1920Z retrovirally transduced CAR. So if we look at day 10, all the CAR design, in the middle, the red, actually, this is our control. So we use the TCR knockout CAR to eliminate the possibilities of what we see of the improved anti-tumor activity for the track CAR is because of the TCR deletion. So we will focus on the blue and the green here, because the red is the same as the green. Both have the same phenotype. So ruled out, the difference we see is because of TCR knockout. So go back to the blue. So at day 10, when we look at the bone marrow, we see that there is comparable levels of T cells here. Oh, excuse me. And the here, the green. So T cell is the same amount. And then in the tumor, we already see that the TRAC CAR-treated mice have less tumor comparing to, a little bit less tumor comparing to the green retroviral transduced CAR. But when we look at day 17, you already see that the retrovirally transduced CAR start to retract. This one also. And correspondingly, we see that the tumor start to escape. However, for the TRAC CAR, you see the tumor control is still very tight. And it's, at the same time, we don't see retraction of the TRAC CAR T cells in the bone marrow. And this is just the facts for the day 17 bone marrow. You see here, there is no tumor. And in both of the retrovirally transduced CAR, there is full of tumor. So by the difference, we think that the difference of the TRAC CAR and the retrovirally transduced CAR anti-tumor difference is because of, by day 17, the retrovirally transduced CAR already become exhausted. So we decided to look at the exhaustion markers of PD-1, LAG-3, and TIM-3, as we hypothesized that the retrovirally transduced CAR, a large percentage of those cells has all three markers, exhaustion markers. However, there is very few cells in the TRAC CAR T cells has these three exhaustion markers. Actually, most of them have only one or zero. So this one has no tumor expression. So no exhaustion marker expression. So by changing the tonic signal control, that we have generated more fitness for the TRAC CAR T cells. We actually had the opportunity, because we are in the academic center which is affiliated to a hospital. So we were able to test all these three concepts in the clinical trials. So the 09114 is the first concept of the conventional 1920 Z CAR. And the 20167 is the concept of the one-axis CAR. And the 22401 is the concept of the TRAC CAR. I want to bring to your attention that for the 1920 Z CAR, alongside with commercial product, the treatment dose level is at least 100 million cells. However, with the 19T228Z one-axis CAR, we have similar comparable clinical benefit when we treat the patient with as little as 25 million CAR. And for the TRAC CAR, in the TRAC CAR, there is an additional step. We also included the one-axis CAR in this trial. We can treat the patient with as few as 10 million cells. So being the bridge between research and clinic, we were the facility have generated all the CAR products used in the clinical trials. And being one of the first in the CAR T cell field, we started our manufacturing using the modular manufacturing platforms, including using the CliniMACS Plus, until we have the opportunity to use the all-in-one solution of the CliniMACS Prodigy. So we actually conducted two side-by-side experiments comparing our modular manufacturing platform and the Prodigy all-in-one solution platform. As you can see that there is a comparable fold expansion and also comparable transduction efficiency when we use when we were doing these comparisons. When we treat the mice, when we put the cells into the mice, we were very encouraged encouraged to see that cells generated from Prodigy has either compatible or even a little bit higher anti-tumor activities. Correspondingly, we also find when we tested during this test that there is a better memory phenotype of the cells generated from the Prodigy. So with that, actually we are preparing a clinical trials targeting CNS lymphoma using CAR T cells produced from Prodigy. And Ivan is the PI. We are working very hard to get this off the ground. CAR T cell therapy is a gene therapy, a cell therapy, and also immunotherapy. So it built upon our knowledge of tumor immunology. It's propagated upon genetic engineering, and it uses a synthetic receptor that repurposes the T cell specificity. And also, to me, I think to most of the people here, is the CAR T cell therapy does not exist if there is no novel and reliable cell manufacturing platforms and devices that we can use. So with that, I want to acknowledge my amazing colleagues, especially Isabel, Michelle, and everyone in the cell therapy and the cell engineering facility, our funding sources, and our industry partnerships, and most importantly, our patients. And thank you all for your attention. I'm happy to take any questions.